Okay, so thanks for the introduction. So I'm going to talk about computational materials discovery, computational materials design, how we actually design new materials. So the basic starting point we have is seen over here on the far left. We start from what we're called structural prototypes. So these are basically different types of underlying commonly observed structures that are in nature. Things like, let's say, the crystal structure of something like silicon, or the crystal structure of something like gallium nitride, which is what's called a wurtzite structure, or gallium arsenide, which is a zinc blende structure, and so on. So then what we do is we decorate these with different elements. So we take let's say, the zinc blende structure. Instead of just having gallium and arsenic, we might put, let's say, silicon and carbon, or silicon and germanium, and so on. Then we take these different structures that have now been decorated, and we calculate it we use what we call density functional theory. So this is a method that sort of simplifies quantum mechanics. And we calculate the energy. So we can calculate where the electrons are, where the electron distribution is going to look like, and also what the energies of the electrons are. So this gives us a set of energies. And then what we can do is we can look at the energy differences between the pure elemental components that make it up and the actual materials that we've calculated. And this is what we call the formation enthalpy. So this is the amount of energy you get out when you say, for example, if you want to take magnesium and oxygen, and you make magnesium oxide, this is the amount of energy you get out. And this tells us something about the stability of this material, how easy it's going to be to synthesize. And we plot this, you see this graph in the middle with delta H versus composition. This actually works. Okay, so we plot this delta H versus composition, and we get we plot delta H as a function of composition, and this gives us, so if you then we plot these, what we call these tie lines around it to give us what we call the convex hull. So if something is on this convex hull, that means it's going to be stable. So the green lines we're going to form green dots here, green X's correspond to stable compounds. If we have something that's above, that's not on the convex hull, let's say one of these red points, these are going to decompose because it's going to be energetically favorable to form the two different components, so you get phase separation. But beyond just stable compounds, we can also say something about disordered materials. So the idea here is if you have a wide distribution of energies, then it's clear which one wants to form. If you have a narrow distribution of energies, then during crystallization, these are going to compete against each other, and you're going to get something like an amorphous structure like a glass. If the structures are similar to each other, and there's a lot of energies the same, then you get a disordered structure, so you get a crystal lattice, but they're occupied randomly, like you have on the right here. And then we can calculate the properties of these disordered materials from essentially a linear combination, a weighted sum, average of the properties of the components. So we get something like a density of states that we see at the bottom. Then we can train all this data, use it to train machine learning AI, and then select new compounds to form and see which ones do we want to calculate next. Okay, so thank you.